Can you all hear us? Great. Welcome. Imagine I'm a customer and I want to buy a product. More specifically, I want to buy a Chromecast. So for the people that don't know Chromecast, that's this product. I like online buying, online shopping, so I start my journey at Google. I type in Chromecast, and this is the result. First of all, it's exactly the product I want, so that's great. But something else is interesting, because all these products are sold across different platforms, but they are somewhat priced the same. And, well, I know Bol, I trust Bol, I also work for Bol, so I get employer discount, so that's great. And I buy the product at Bol. I'm a happy customer. So then, for my second product, I want to buy a mirror. I type in, actually because of my previous experience, I start immediately my journey at Bol. I type in the mirror I want, and now this is the result I'm getting. Multiple listings on what seem to be the same product, but with a wide variety of prices. This, of course, as a customer, leaves me very confused and maybe even angry. So then, for a third product, I want to buy a PlayStation 5 cover. I start my journey back at Google because of the previous experience I had with Bol. So then, now this is the result I get. Again, it's the product I want, but now something else is happening. Compared to the Chromecast, the prices are much different. So the product at Bol is much more expensive compared to the other platform. And of course, even with my employer discount, I would be better off buying the product at the other platform. And of course, this is not a good experience and would maybe even, me as a customer, start my next journey at this platform. My name is Thijs, and together with Gokhan, we will show how we created a pipeline that will help us build, well, actually price competitively, find duplicates on our website, but also inspire you and hopefully lower the barrier of using these kind of technologies. First, a very small introduction. So, both Gokhan and I are data scientists working for Bol. We are a platform, an online e-commerce platform that sells roughly 40 million products across roughly 50,000 different partners. This is of course an immense scale, and that means that every solution we build needs to be very scalable. This is all the context you need, and now we can dive into real cool stuff, and that's where Gokhan will start.
Thanks, Thijs. Can you all hear me well? Cool. I want to start with a bit of a personal story. So this happened to me recently. First, this is a photo of my living room. I live right over there. I live in Buitenveldert, so I'm quite close to here. As you can see, this photo was taken in summer because there's a lot of sunlight. And another thing that you might notice in this photo is that I have a lot of plants. I really like plants. I get them gifted by friends. I name my plants. And knowing this, my friends also come to me for plant advice. And recently a friend reached out to ask for a beginner-friendly plant package that also was well priced. Well, I redirected them to this listing that is on our platform. From personal experience, I know that these are easy to take care of plants, and because I work in the pricing domain, I know that this is a good price. And indeed, if I were to go on Google and search for the same product, from a competitor, we get the exact same price as well. How do we do this and why do we do this? Well, we have a bunch of partners that are selling on our platform, and we would like to keep our prices competitive, so we have certain pricing policies. And these pricing policies also depend on the prices across other platforms. But to do this, one thing that we need is we need to know that these products are the exact same product. And we currently do that with something called an EN. And an EN is a European article number. These two products on these two platforms will share an EN, and based on this EN, we actually can say that these products are a match, and we can get pricing information. This past winter, so a couple of months ago, I realized how dark it was going to be, and my plants needed some extra light, some extra love. So I started looking for growth lamps, and I started on our platform, and I saw this lamp being sold for 120 euros, which seemed a little bit steep to me. So I know what to do. I can look for the EN of this product, and I can go on Google to search. But this result returned nothing. How can this happen? Especially if I were to look for this exact plant lamp and I can find it on a competitor platform. Again, we have a bunch of sellers on our platform, and these sellers can either mistakenly put a wrong EN so that we cannot match them, or they can intentionally put a wrong EN so that they get around these pricing policies. However, this is still something that we would like to prevent, because from a customer's perspective, these two are the same products, and we would like to not have a bad price perception. Thankfully, the EN is not the only information that we have about a product, and this is where data science steps in. For a product, we have a variety of information, and this can come in terms of the product image, the product title, the product description, and even the attributes. And we have developed a pipeline to be able to match products, not only having to rely on the EN, but using this unstructured data. Before I start with the pipeline definition, I first would like to give a bit of a technical background into some technologies that we use. And the first of them is called embeddings. Now, by show of hands, who here have heard of or worked with embeddings before? OK, that's around half. For the rest, I will give a very brief explanation of what they mean conceptually. Now, if I were to think of an embedding is a representation of an entity, a vector representation or a numerical representation of an entity, such that two vectors that are close to each other also share a semantic similarity. So if I were to show this in examples, here you see a green plant that's currently plotted at 2,4 on the top right quadrant. And if I were to plant even more plants in this vector space, you can see that green indoors plants, which are semantically close to each other, are on the top right quadrant. And the green outdoors plants are on the top left quadrant. So the plants that make sense to be together in this semantic space, where we have outdoors to indoors on the x-axis and red to green on the y-axis, they are clustered. And indeed, if I were to look at the vectors, you see that these two plants have vectors that are close to each other. Whereas these two plants, while they still share similarity on the outdoors axis, they are further from each other compared to the color axis. And they are a little bit different, even with vector similarity. And these two plants are actually quite different from each other. So the vector similarity in this case would be quite low. And we can use this technology and this concept to define the similarity of images or text in a numerical format. And basically, this allows us to create embeddings for our catalog. But what we showed is just in a 2D space, so this is just to make it a lot more understandable. How we actually create and how we actually calculate embeddings is by using a transformer architecture. And we use a transformer model. And for our use case, we use the vision transformer model that you can very easily get from Hugging Face. We take the output of the last step, and this contains a lot of semantic information about these images. With this, we actually can embed and get numerical representations of all the images in our catalog. Now that we have these embeddings, we have a way of finding similarity between these images. What we would like to do next is to perform search through them. So imagine that we have our embedding space, our catalog, completely represented. And in the real world, we have 768 dimensions per vector. And of course, number of rows is the number of images in our catalog. What Thijs shared with 40 million products, on an average of 5 images per product, we already get above 200 million images. So this is a very large space to search through. And if we were to have a query vector, in this case, the query vector, for example, would be a competitor image, you cannot do this brute force. This is not efficient. This is not, we cannot do this at scale. especially at a scale of more than 200 million embeddings. So we need something smarter. And this is where approximate neighborhood search algorithms and vector databases and vector database libraries that provide this functionality come into play. To show how one of these algorithms work, I would like to take you through this simple example. So if you were to think of our catalog in terms of these 500 vectors in a 2D space again, and we would like to search with a query vector that you can see with red. What we cannot do, because it's too large, is, again, do brute force. But what we can do is rely on some smart algorithms. And one of these algorithms, called inverted file index, would cluster the embeddings that we have in this vector space. Then we can calculate the centroids of these clusters. And then we can compare our query vector only with the clusters, with the cluster centroids, so that we know which cluster to look into. And here you see that already my search space is down to 1/5, because I will only look at the cluster that is the closest to the query vector. If you take this idea and if you scale it up, then you get an idea of how much more efficient this actually is. And for this, we rely on Thijs, which is a vector search or an approximate neighborhood search library provided by Facebook. And this is how we scale up our vector search. The last part that we need to be able to search through is, of course, a query vector. And as I said, the query vectors actually come in form of competitor images. So we take the competitor images and we put them through the same transformer model that we used to embed our catalog images, and then we reach at a query vector. Then what we can do is, with this query vector, we can search through our database, and then we get some nearest neighbors, some candidates that we think, OK, these products can actually be a match. However, after getting these candidates, how do we actually get a precise product matching? That is what Thijs will explain next.
Yes, thank you. Indeed, because if we go back to the first problem, we are, of course, interested in knowing which products are the same, so we can actually determine, OK, to be price competitive, we want to know, like, OK, which products are the same and which should be priced the same. Whereas just solely focusing on image, this may not be enough. What could happen, for example, if you look at the first one, so we are searching with the left one and we get back the top one, but this is actually a bundle. So it also adds two plans, for example, which is on the price scale, it could allow for a higher price or a lower price. Same for the second one. There is a difference in wattage, which could also mean a different price. Whereas the third one then would mean an exact match, and the fourth one mean, again, this would be a different match. So, of course, we are performing at such large scale that we cannot do this manually. We cannot compare each match like, OK, are these the same products? So what we did, we created a classification model that just looks at the title. So we have the candidates based on image, and then we have just a classification model that will compare each candidate with the query factor. What does that mean? Well, the first row, it would compare this title with the match title. We have a classification model, and this say, this is not a match. And then for the second one, again, it would determine, is this a match, yes or no, etc. These examples are very easy. I don't even think we would need the classification model. Regex would be sufficient. But of course, on our platform, our titles look much more like this. So there is way more noise around it, and only a few parts matter. Like, we need to learn which specifications matter for price. And that's exactly what we did. So again, we used the transformer architecture, and we trained a model that was able to learn which parts of the title I should pay attention to and which parts I can ignore. So for this title, it would learn the following. It would remove the marketing terms. It would learn that this is not needed, and then it would focus on the specifications. So this helps us really well for price comparison. Now, to give you an overview of the whole pipeline, we start with a competitor image. This is our query factor. We put it through a vision transformer, and we get an embedding. Then this embedding, we will search through the database that we also have all images of our platform embedded, and we get candidates. So you can think about these are the top 5 candidates, the top 10 candidates. You can specify how many you want to get back. And then we'll use this in our title classification model to determine if these are exact matches. This solves the first issue of price competitiveness. But we also showed the duplicate issue. And actually, we figured out that by just changing one component here, we could also solve this. What we did is, instead of searching with the competitor image, we searched with the ball image. Of course, your first result, hopefully, is the exact same product, because then you know your pipeline works. But it's really interesting to look at the other results. Because, well, of course, they could be the different specifications issue I just described. But if also the title model says it's an exact match, something interesting is happening. Because then we have duplicates. And that's exactly how we found these. So currently we are already in the process of removing these or merging these, because then our platform can really operate how it should, right? They have offer pressure, they are competing for the same buy block, and that's exactly what we want for Bol. After this, we also looked in other output of our pipeline, because we think there is a lot of value in this data and in each separate process of this pipeline. The next thing we looked into is just embeddings, because as Gokhan explained really well, there is semantic meaning in here. And we thought this can benefit other problems as well. One of the issues we see on our platform sometimes, again, because we are having such a large scale, this can happen, is this. So I search for a shoe, and this is the primary image. It's a size table. That's not helping the customer. I don't know what type of shoe I'm buying here. Whereas the product has better images available. So we thought, by looking at the embeddings, we now know what the semantic meaning of each image is. So we also can maybe detect these kind of outliers. So how would we do this? Well, again, now showing 2 dimensions, because 768 is not plottable. But it will help you understand how we do this. So we embed each image. And if you would then plot them, like this, it's really easy to detect the outlier. And that's what we did, and that's how we indeed first created a list of, hey, these are outlier images, these are primary images. Maybe we want to check them. But this is not where we stopped, because we felt like we have so many products, we also need to suggest them then a better image. And that's what we did. We even optimized now. So what we did, this is currently our sneakers list page. It's not bad, right? At least no size table, so that's great. But it can be a bit noisy. So sometimes we have 2 shoes, sometimes we have 1 shoe, we have a shoe pointing to the left, shoe pointing to the right. Whereas we would like to suggest the following. This gives uniformity and hopefully improves conversion. And that's all possible with the data points that we are creating now. A machine can understand these and can even optimize now. So currently we are running tests to see indeed if this helps the customer in their selection of the product. Now, for our final use case, I will hand it over back to Gokhan.
Thank you. Now for this final part, I need a little bit of audience participation. I would like everyone to take their phones out. And I would like for you to search for the following product. Now I'll give you a bit of a hint. This is an ice block maker, so that you can put it in your freezer. And I will give you 30 seconds to see if you can find this product on our platform. Hopefully you have the app. Fingers crossed. I still see people searching. By a show of hands, has anyone been able to find this product? Or something similar? Close enough, close enough. Well, we saw that this was a bit of an issue because this was actually quite a popular product and it was popular on TikTok. So a lot of people were actually buying this on our platform. But it is a bit of an obscure thing to search for and to find. But here's how we would do it internally. So you can see that we can copy this product image. And we have built an internal tool to take the vector search, take the image search part into real time. So that this allows our colleagues, our internal colleagues, to do visual search for popular products, for products that they want to find similars of. And this greatly benefited our customer journey and promotion specialists, and it's currently available for our internal colleagues. But this was a very nice byproduct of how we used our pipeline and what we built. To give a final overview, we started quite simple from looking at images. Then we use a transformer model that we can get off the shelf to reach at embeddings. We can build vector indexes on these embeddings that is easily searchable. Then we get some candidate products and candidate images from these embeddings. And we can use our title similarity model to make precise product matches. You see that our pipeline is greater than the sum of its parts, but its parts are quite simple and its parts are quite easily accessible. So we hope that this presentation and our use case has inspired you to use these technologies in your company or in your personal projects. And we would like to thank you for coming to our talk. And if you have questions, feel free to ask them.